Hello, welcome to our research on long rod dexterous manipulation and force-based search for peg and hole location uncertainty. This research focuses on how long objects, which are not found to be addressed directly in other research, can be dexterously manipulated by a robotic arm and a specific algorithm that solves the infamous peg and hole problem. The first part of the paper details the search for the hole via the booster feed-on motion, also known as the spray painting method. For the insertion of the object to be successful, we must be able to identify the location of the hole consistently and reliably. The arm moves in this motion and uses a built-in force-torque sensor to map its environment. First, the arm maps this environment by identifying the x, y, and z coordinates of the tabletop through dramatic changes in the force in one coordinate direction. Then it uses the booster feed-on motion to map the coordinates of the edge of the socket. Next, after a calculated rotation of 90 degrees, the user hands the rod to the gripper at an unknown value of Lg. The rod is then moved down until a force is detected and the value of Lg is calculated from this height coordinate minus the height of the socket relative to the tabletop. As mentioned, Lg is the length from the center of the grip to the bottom tip of the rod. After the hole's location has been identified, the insertion algorithm takes over. Traditional methods used to address the peg and hole problem focus on exact locations and tight tolerances, which often cause excessive forces as the arm tries to insert the object at the wrong location. This leads to jamming and a high probability of damaging components. Our algorithm solves this by manipulating the object after adding a new degree of freedom. The force of the gripper is loosened from 20 to 0 newtons, which adds another degree of freedom to the system through the new compliance in the joint between the rod and the gripper. The gripper then moves backward, and the friction and normal force on the rod cause it to rotate in the gripper. We can determine the angle of rotation through simple trigonometry and moving the gripper down and back according to distances dz and dx. Finally, the arm moves toward the socket, scraping the angled rod until it registers a high change in the TCPZ direction. The contact force signifies the edge of the hole's countersink. From here, some adjustment code uses the normal force of the countersink's edge to rotate the rod back to vertical as the gripper moves forward. Once the sensor is confident there is no jamming or excessive force, the rod insertion is complete. This video shows a run that was considered to be almost successful since the rod is vertically in the hole but not completely inserted by the robot. To prove the efficiency of the algorithm, several values of Lg were tested. This chart shows a green S for successful insertion, a yellow A for almost, and a red N for not successful. At the most successful length of 20 millimeters, the method was 80% efficient. This value is comparable to about 80% efficiency of similar methods, like Dr. Masahiro Ohaka in 2017. However, unlike previous research, our method requires no custom grippers or need to train a neural network. The robot overcomes its factory limitations by introducing a new degree of freedom to the system and manipulating the rod with external forces. Thank you for watching.